Hi, welcome back to educator.com. Today we're going to talk about rational functions and vertical asymptotes. The next few lessons are going to be about rational functions and asymptotes, and they're pronounced asymptotes. They're spelled kind of funny, A-S-Y-M-P-T-O-T-E-S, but we want to know how to pronounce them. They're pronounced asymptotes. In exploring these ideas, we'll see some very interesting behavior and we'll learn why it occurs. But before you start these lessons, it's important that you have a reasonable understanding of polynomials. Polynomials are going to be central to this, as we're about to see in the definition of a rational function. You'll need to know their basics, you'll need to know how to factor them to find zeros, roots, and you'll also need to know polynomial division. If you haven't watched the previous section of lessons on polynomials, you might find it helpful to watch the 3 lessons: Introduction to Polynomials, Roots, Zeros of Polynomials, and Polynomial Division, or just the ones that you need specific help with, because those ideas are going to definitely come up as we explore this stuff. Also, it should be mentioned that we'll be working only with the real numbers, so we're back to working just with the reals. And while we briefly worked the complex numbers in the last couple lessons, it's back to the reals. We're not going to see anything other than real numbers anymore. So if we would have solutions in the complex, oops, too bad. We're not going to really care about them right now. So we're back to focusing just on the reals. They're still pretty interesting, lots of stuff to explore in the reals, so you can leave complex numbers to a future, later course in math. All right. First, let's define a rational function. A rational function is the quotient of 2 polynomials. So f of x is a rational function. It's equal to n of x divided by d of x, where n of x and d of x are both polynomials, and d of x is not equal to 0. And by not equal to 0, I mean that d of x, isn't 0, like straight up, this is 0 all the time forever. So d of x equals 0, the constant function, just, 0 all the time forever, that is not allowed. But d of x can have roots. We can say that d of x can have roots. Like, for example, d of x could be x squared minus 1, where d would be, d would be 0 at positive 1 and negative 1. That's okay. D of x can have roots, but it's not going to be the constant function of 0 all the time. That's what's not allowed, because then our function would be broken completely everywhere. But we are allowed to have slight breaks occasionally when we wind up having roots appear in the denominator. So just a normal polynomial, but not just 0. That would be bad. All right, so some examples: g of x equals 2x plus 1 over x squared minus 4, or 1 over x cubed, or x to the 4th minus 3x squared over x plus 2. In all of these cases, we've got a polynomial divided by a polynomial. Simple as that. You might wonder, why are they called rational functions? What's so rational about them? Remember, many lessons back, when we've talked about the idea of sets, we called fractions made up of integers, things like 3/5 or negative 47 divided by 2, the rational numbers, because they seem to be made in a fairly rational, sensible way. Thus, we're using a similar name because the rational functions are built similarly, right? Rational numbers are built out of division, and rational functions are built out of division, so we're using a similar name. Cool. Since a rational function f of x equals n of x divided by d of x is inherently built out of the operation of division, we have to watch out for dividing by 0. That's going to be sort of the Achilles heel of rational functions, and also is going to be what makes them so interesting to look at. Dividing by 0 is not defined. It's never defined. So the zeros, the roots, the places where it becomes 0 of our denominator polynomial, d of x, will break the rational function. The zeros of d of x are not in the domain of our function. So a rational function, right here, wherever it winds up being 0, it's not defined there. That's not in the domain. It's not in the set of numbers that we're allowed to use, the domain, because if we plug in a number that makes us divide by 0, we don't know what to do. We just blew up the world, so it's no good. So we're not going to be allowed to plug in numbers. We're not going to have those in our domain when d of x equals 0, when we're looking at the zeros, the roots of our denominator polynomial. Now, other than these zeros in the denominator, a rational function is defined everywhere else, right? Because polynomials have all of the real numbers as their domain. Since you can plug any real number into a polynomial and get something out of it, the only place we'll have any issues is where we're accidentally dividing by 0. So everything other than these locations where we divide by 0, they're all good. So the domain of a rational function is all real numbers except the zeros of d of x. So all real numbers with the exceptions of these zeros in our denominator polynomial. Everything will be allowed with a very few exceptions for that denominator polynomial zeros. All right. To help us understand rational functions better, let's consider this fundamental rational function, 1 divided by x. So immediately we see that f is not going to be defined at x equals 0, right? So our domain for this will be everything except x equals 0. So domain is everything where x is not 0, so most numbers. We see that we can't divide by 0, but everything else would give us an actual thing. So notice how it behaves near x equals 0. So it isn't actually going to be defined at x equals 0. We'll never see that. But as it approaches it, f of x grows very, very large. See how it's shooting up, right? We've got that going up and down very, very large. So what's going on here? Let's look at a different viewing window to get a sense for just how large f of x manages to become, right? If we look at a very small x width, only going from negative 0.5 to positive 0.5, we manage to see a very large amount that we move vertically. We can go all the way, as we come from the left, we manage to go from, near 0 all the way to negative 100 on this window. And we can go from near 0 all the way up to positive 100 on this window. And in fact, it will keep going. It just keeps shooting up. It shoots all the way out to, well, not out to infinity because we can't actually hit infinity, but the idea of shooting out to arbitrarily large. It's going to get as big as we want to talk about it getting out to. So in a way, we say it goes out to infinity. We see this behavior of blowing out to infinity in many rational functions. If we look at 1 over x plus 2, we get it blowing out to infinity at negative 2. Notice that when we plug in negative 2 into the denominator, we'd have a 0 showing up. So we see this behavior near round zeros. If we look at 5 divided by x squared minus 9, we see it at negative 3 and positive 3. So we have these places where it blows out to infinity. In a few moments, we'll formally define this behavior and we'll name it a vertical asymptote. But first, let's understand why this strange behavior is occurring. To understand that, let's look once again at f of x equals 1 over x, our fundamental rational function, sort of what makes up the most basic form of it. Notice that while x equals 0 is not defined, right? That would blow things up because we'd be, blow up the world because we're dividing by 0. We're not allowed to do that. It just doesn't make sense. But everywhere else is going to be defined. So let's see what happens as x goes to 0. This little arrow, we say x is going to 0. We're looking as x gets close to 0. Not actually at 0, but as x sort of marches towards 0. So let's look what happens as we go from the negative side. As we plug in negative 2, we'd get negative 0.5, right? 1 over negative 2. We plug in negative 1, we get negative 1. But as the x becomes very, very small, we see f of x become very, very large, right? Negative 0.5 gets us negative 2. Negative 0.1 gets us negative 10. Negative 0.01 gets us negative 100. Negative 0.001 gets us negative 1,000, right? As we divide a number by a very small number, right? 1 divided by 1/10 is equal to positive 10 because the fraction will flip up. And we're going to wind up having to look at its reciprocal since it's in the denominator again. So we're going to see this behavior of as we get really, really small, as we get to these really small numbers that we're dividing by, we'll wind up having the whole thing become very, very large. We can see this on the positive side as well. If we go in from the positive side, right? So the negative side is us starting from the negative side and us moving towards the 0. And the positive one is us starting from the positive side and us moving towards the 0. So moving from the right into the left versus moving from the left into the right. Positive, if we look at 2, we get 1/2, 1 over 2. We plug in 1, we get 1 over 1, so 1. As we get smaller and smaller, we see it begin to get larger and larger. We plug in 0.5, we'll get 2. We plug in 0.1, we'll get 10. We plug in 0.01, we'll get 100, and so on and so forth. As we get in smaller and smaller and smaller numbers, we're going to get larger and larger things, right? 1 over 1 divided by 1 million, very small number, but it's one of the things that's defined, right? Because it's not x equals 0, it's just very close to x equals 0, will cause it to flip up to the top and we'll get 1 million. So we'll get to any size number that we want. We can't actually divide by 0, but by dividing by very small numbers. So dividing by very small numbers gives large results. So this is what's happening. As we get near 0, we blow out to infinity because we're dividing by very, very small numbers. And when you divide by something very, very small, you get a very big thing, right? How many times does something very, very small go into, a reasonable size number? It goes in many times. The smaller the chunk that we're trying to see how many times it fits in, the more times it's going to be able to fit in. So the smaller the thing that we're dividing by, the larger the number we'll get out in response. And that's what's going to cause this behavior of blowing out. So with this idea in mind, we'll define a vertical asymptote. A vertical asymptote is a vertical line x equals a, where as x gets close to a, the size of f, the absolute value of f of x, becomes arbitrarily large. It becomes very big. Symbolically, we show this as x goes to a will cause f of x to go to infinity or f of x to go to negative infinity. Informally, we can see a vertical asymptote as a horizontal location a, some horizontal location a, where the function blows out to infinity, either positive infinity or negative infinity as it gets near a. So it's going to be some location, right, some location a, that as we get close to it, we go out to infinity, right? We manage to blow out to infinity as we get close to it. We get very, very large numbers. So a vertical asymptote is some horizontal location, some vertical line defined by x equals a, where as we get close to it, we blow out to infinity. Maybe we blow up, maybe we blow down, but we're going to blow out to infinity one way or the other. Vertical asymptotes and graphs. We show the location of a vertical asymptote with a dashed line, as we've been doing previously. This aids in drawing the graph and in understanding the graph later. So notice we just use a dashed line here to show us this is where the vertical asymptote is. So for the graph of f of x equals 1 over x minus 1, we see right here at x equals positive 1, because if we plug in x equals positive 1, we'd be dividing by 0 there. So near that location, we will be dividing by very small numbers, which will cause us to blow out to infinity around that location. We'll see a vertical asymptote there. So as our function approaches that vertical asymptote, it winds up having to get very, very large because it's now dividing by very, very small numbers. Notice that the graph gets very close to the asymptote, but it won't be able to touch the asymptote. So it will become arbitrarily close to the line, but it never touches the line. Why can't it touch the line? Because it's not defined there, right? We've got 1 here. So if we plug in x equals 1, then we've got 1 over 1 minus 1, which is 1 over 0. Hey, we're not allowed to divide by 0, so we're not allowed to do this, which means we're not allowed to plug in x equals 1. Our domain is everything where x is not equal to 1, so we're not defined at that thing. Our function is not actually defined on the asymptote. It will become very large, it will become very close to this asymptote, but it won't actually be allowed to get onto the asymptote, because to be on that point, to be on that horizontal location, would require it to be defined there, and it's not defined there because that would require us to divide by 0, which, not allowed, so we're not allowed to do that, which means that we're not actually going to be able to get on it. We'll never touch the vertical asymptote because it's not defined. Now, not all zeros give asymptotes. So far, all of the vertical asymptotes we've seen have happened at the location of a 0 in the denominator. And that is going to be the case. All vertical asymptotes will require there to be a 0 in the denominator. But a 0 in the denominator does not always imply an asymptote. So we're not going to always see an asymptote. Consider f of x equals x over x. Now normally, x over x is a very boring function, right? The x's cancel, and we're left with this effectively being just 1, right? Except at one special place. When we look at x equals 0, we're given 0 divided by 0. Now 0 divided by 0, definitely not defined, so we're not allowed to do anything there. We have a pretty good sense that, yeah, it would be going to 1, but when we actually look at that place, it's not defined because we're looking at 0 divided by 0. 0 divided by 0, definitely not defined, so where there's going to be a hole in the graph. So f is a rational function, x divided by x, polynomial divided by polynomial, simple, constant, linear, not constant, but simple linear polynomials, but they're both polynomials. So f is a rational function, and it's not defined at x equals 0, but it still has no asymptote there, because normally we've just got x over x is just really a constant function 1, right? We see it here, it's going to be 1 all the time, forever, always, except when we look at x equals 0, at which point it blips out of existence because it's not allowed to actually have anything at 0 over 0 because that's not defined. So formally, we can't give it a location. So instead, we have to use this hole. We show that there is a missing place there with this empty circle, right? As opposed to a filled-in circle to show that there's something there, we use an empty circle to show that we're actually missing a location there. So it has a hole at that height there because it would be going there, but it doesn't actually show up there. So there's no asymptote there. Why does it happen? Why do we lack this asymptote? Because the numerator and the denominator go to 0 at the same time. So the asymptote never happens. Because they're both going to 0, there's nothing to divide out to blow up to a very large number or to blow down to a very large negative number. The asymptote can't happen because normally they just cancel out to 1 over 1, right? Well, not 1 over 1, they cancel out to something over something, but since it's the same something, it becomes just 1. So if we've got 0.1 divided by 0.1, well, they cancel out and we just get 1. If we've got 0.00001 divided by 0.0001, well, once again, they cancel out and we've got just 1. So we don't wind up seeing this asymptote behavior because we've got to have something divided by very small numbers. But if we've got very small number divided by very small number, they wind up going at the same rate, and so we don't get this asymptote. To find an asymptote, then, that means we first need to cancel out common factors. We need to be able to see, oh, hey, x over x, that means I'm going to cancel these out, and I'll get it to be equivalent to being just 1. We'll have to remember that we're forbidden to actually plug in x equals 0, but other than that, it's just going to be 1 all the time, forever. So with our newfound understanding of all these different things that make up rational functions, we can create a step-by-step guide for finding vertical asymptotes. So given a rational function in the form n of x divided by d of x, where n and d are both polynomials, the first thing we want to do is we want to figure out all the x values that we aren't going to be allowed to have in our domain, all of our forbidden x values that would break our function. So these are the zeros of d of x because they would cause us to divide by 0. Since dividing by 0 is not allowed, then our domain is everything where we won't divide by 0. So the zeros of d of x are not in our domain. Next, we want to determine if n of x and d of x share any common factors. So to do this, you might have to factor the two polynomials. If they share common factors, cancel out those factors. Alternatively, this step can be done by checking that the zeros to d of x are not also zeros to n of x, right? Because for them to have a common factor where they would both be going to 0 at the same time, then a common factor means that they have the same root. So if they are both going to be zeros at the location, that means we'll see this effect. So we can either cancel out the factors or we can just check and make sure that the roots to d of x are not also roots to n of x. But the easiest way to find roots in the first place is usually to factor, so you'll probably want to factor for the most part, but occasionally it will be easier to just see, hey, if we plug in this number, does it come out to be 0? Next step, once you've canceled out the common factors, you determine any zeros that are left in the denominator. These are the vertical asymptotes, because once we've canceled out common factors, we don't have to worry about them both the top and the bottom going to 0 at the same time, so any roots that are left going to have to make very small numbers to blow everything out to infinity. So anything that's left after canceling out, it's crucial that it's after you cancel out common factors, whatever is left as zeros in the denominator after canceling out will give you vertical asymptotes. Finally, an optional step, if we're graphing the function, you want to figure out which way the graph goes, positive infinity or negative infinity on either side of each asymptote. You can do this by using test values that are very close to the asymptote. For example, if we had an asymptote at x equals 2, we might want to check out f at 1.99 and f at 2.01. They're very close to the asymptote, so we'll have an idea of where it's going. Alternatively, you can also do this in your head by thinking in terms of positive versus negative and just thinking, if I was very slightly more or very slightly less, and we'll discuss this in the example, you'll see it specifically in example 3, we'll see this idea of if I was just a little bit over, if I was just a little bit under, and it'll make a little bit more sense when we actually do it in practice. But you can always just test a number, use a calculator, figure out, oh, that's what that value would be. I'm clearly going to be positive on this side. I'm clearly going to be negative on this side. All right. Let's look at some examples. So f of x equals x minus 1 divided by 2x squared plus 8x minus 10. What is the domain of f? So to figure out the domain of f, we need to figure out where are zeros on our bottom, right? Where are the zeros on our bottom thing? So our very first step will be to factor 2x squared plus 8x minus 10. So how are we going to factor this? Well, let's start out by pulling at that 2 that's in the front, just kind of getting in our way. So x squared plus 8x pulling out of 2 becomes 4x. Negative 10 pulling out of 2 becomes negative 5. We can check this. If we multiply back out, we see we have the same thing. So 2 times x squared plus 4x minus 5. Can we factor this further? Yeah, we can. We see that if we have positive 5 and negative 1, that would factor. So 2 times x plus 5 times x minus 1. Sure enough, that checks out. X squared minus x plus 5x, because that checks out the 4x, plus 5 times negative 1, negative 5. Great. So that checks out. So that means we can rewrite x minus 1 divided by 2x squared plus 8x minus 10 is equivalent to saying x minus 1 over the factored version of the denominator. 2 times x plus 5 times x minus 1. So all the places to figure out the domain of f, all the places where our denominator will go to 0 is going to be x at negative 5 and x at positive 1. Now we don't want to allow those, so when x is not negative 5 and x is not 1, then we are in the domain. We're allowed those values. So our domain is everything where x is not negative 5 and not positive 1. Great. Next question is, where are the vertical asymptotes? To find the vertical asymptotes, we need to cancel any common factors so that the numerator and the denominator don't go to 0 at the same time. We notice we've got x minus 1 here, x minus 1 here, so we can cancel these out, and we get 1 over 2 times x plus 5. So now we're looking for, where does the denominator go to 0? So where's the denominator go to 0? That's going to happen at when is x plus 5 equal to 0? So we get x equals negative 5. So we've got a vertical asymptote when the denominator in our new form with the common factors canceled out. So we'll have a vertical asymptote after we've canceled out common factors when we can figure out the denominator still goes to 0. So at x equals negative 5. Great. Second example. Given that the graph below is of f, our function, find a and b. If our function f is 3x divided by quantity x minus a times quantity x minus b. So we notice, first off, hey, we've got a vertical asymptote here and a vertical asymptote here off of this graph. So we see one of our vertical asymptotes happens at negative 3, the other one happens at positive 2. So x equals negative 3, x equals positive 2, we've got vertical asymptotes. Okay, so if x equals negative 3 and x equals 2 means vertical asymptotes, then that means we need to have a factor that will cause a 0 in the denominator at those locations. So we want a 0 in the denominator at negative 3, so x plus 3 would give us a 0 when we plug in negative 3. And x minus 2 would give us a 0 when we plug in positive 2, right? Plus 3, we plug in negative 3 plus 3, hey, that gives us a 0 in our denominator. Plug in positive 2, 2 minus 2, hey, that gives us a 0 in our denominator. Great. So that means that x plus 3, x minus 2, we need those factors in our denominator to be able to have vertical asymptotes. We don't have to worry about it interfering with our numerator because 3x doesn't have any common factors with x plus 3, x minus 2. They're very different linear factors. So at this point, we're ready. So we want minus a to be plus 3, so that means that a must be equal to negative 3 because it comes out to be positive 3. So there's our a. And b minus b, so negative 2. So it must be that b is equal to positive 2 because it's still actually subtracting. And there are our answers. All right. Third example, draw the graph of f of x equals 1 over 3 minus x. Pretty simple one, so we don't have to worry about factoring. Already been factored. We don't have to worry about canceling any common factors. We see that it's very clearly no common factors, so we can just get right to figuring this out. So we've got a vertical asymptote. First, we notice that we've got a vertical asymptote at x equals 3. Because when we plug in 3 minus x, we've got 3 minus 3, so we'd have a 0. So we'd be dividing by very small numbers. We'd be dividing 1 by very small numbers at x equals 3. So that means we will blow out when we are near x equals 3. So we've got a vertical asymptote there. Let's draw in our graph axes. So let's put this at, we'll need more to the right because the interesting thing happens out here. So here's 1, 2, 3, 4, 5, we'll extend that a little bit further, 6, 1, 2, 3, 4, 5, 6, go for roughly the same scale. Okay, and 1, 2, 3, -1, -2, -3, -1, -2. Great. So we've drawn out our graph. And we know that we've got a vertical asymptote at 3, so let's draw in a vertical line. Okay. So we see our asymptote on our graph. And now we need to draw it in. So at this point we realize, oh, we actually probably should have some points, so let's try some points. If we try x equals, oh, let's say 4, right? Just a little 1 unit to the right of our asymptote. So we plug that in, we'll get 1 over 3 minus 4, so 1 over 3 minus 4, which gets us 1 over -1, so 1 over -1, -1, so at 4 we're at -1, so we plot in that point. Let's try 1 unit to the left, x equals 2. We'll get 1 over 3 minus 2. So we'll get 1 over +1. 3 minus 2, +1. So we'll be at +1 when we're at 2. We might still want a little bit more information. So maybe we'll also try like x equals 0. At x equals 0, we'll get 1 over 3 minus 0. So we'll be at 1/3. So at 0, we're just 1/3 of the way up to our 1. So we'll put in that point there. At x equals 6, let's try that one. We'll be at 1 over 3 minus 6, so 1 over -3, so we'll be at -1/3. So once again, we'll be just a little bit, 1/3 of the way out there. All right, so now we're starting to get some sense. Well, what happens as we actually get near that asymptote, right? Are we going to go positive on the left side? Or are we going to go negative on the left side? Are we going to go positive on the right side? Or are we going to go negative on the right side? So what we can think about is we can consider just a hair to the left of 3. Consider 2.9999, right? Consider this number. Now, we could actually plug it into a calculator and we could get a value, but we can also just think about this in our head and say 1 over 3 minus 2.99999. Well, 1 over 3 minus 2.99999, right? If we've got a bunch of 9s, 3 minus 2.99999, well, is it going to be a positive number or is it going to be a negative number? Well, 3 minus 2.999, 2.999, it's still smaller than 3, so it's going to come out as a positive thing. So we've got 1, a positive number, divided by a positive number, right? We can just think of it, hey, we're dividing by a small positive number, so that means the whole thing will come out to be a positive thing when we're on the left side, because we're subtracting, but it is, we're subtracting by something, but it winds up being just under, so we stay positive. So we can think in terms of, oh, are we being positive? Are we being negative? We're being positive, so we know we're going to go up on this side. If we consider a very small number above 3, 3.00001, if we consider that will be 1 over 3 minus 3.00001. Well, 3 minus something that's just a little bit above it, that's going to wind up being negative. It's going to be a very small number, but it's going to be negative, and that's key. So 1 over a negative number on the bottom. Since it's a positive divided by a negative, the whole thing will stay negative, and so we'll get very large negative numbers, so we'll be going down on the right side. So at 3.00001, we see that we wind up being still negative, so we'll have to be negative when we are on the right side of our asymptote. On the left side, 2.99999, just to the left of our asymptote at x equals 3, we see that we're going to wind up being positive, and so that guides us on how our asymptote should grow. So at this point, we can draw in this curve. It's going to be growing and growing and growing. And as it gets to the asymptote, it's going to get larger and larger and larger and larger and larger. It will never actually touch the asymptote. It will wind up just getting larger and larger and larger and going up and up and up. It never becomes perfectly vertical. It never touches the asymptote, but it's going to blow out to infinity slowly but surely. It won't ever actually touch infinity because we can't touch infinity. Infinity is just an idea of ever larger numbers, but it will go out to ever larger numbers. On the other side, we see very similar thing. So that should be curved just a little bit more, not quite straight. And it's going to get very, very large, and once again going to curve out. Never quite touches that vertical asymptote, but we'll get very, very, very close. My right side is a little bit closer to the vertical asymptote than it probably should be, but we have a good idea that'd be acceptable when turning that in on a test or homework. What happens as we go very, very far to the left? Well, let's think about as we plug in some really big negative number, like say -100. Well, at x equals -100, we're going to wind up having 1 over 3 minus negative 100. Those cancel out. We get a positive, so we get 1 over 103, which is a very small number. So since it's 3 minus x, as we plug in very large negative numbers, we're going to effectively get very large positive numbers in our denominator, and so we'll be dividing by very large things, so we'll sort of crush down to nothing. So as we get larger and larger and larger, we're going to slowly approach 0. We'll never quite hit 0. We'll talk about this more when we talk about horizontal asymptotes in the next lesson, but we'll get very, very close to the 0 height. Same thing as we go out to the right. But we'll be coming from the negative side, because if we look at a very, very large positive number like 1 over 3 minus 100, a positive 100 plugged in for x, we'll get 1 over negative 97. So it will be a very small number, but will be a very small negative number because we've got that negative on the bottom. And so we'll be on the bottom side. We'll be below the x-axis. Great. Final example, example 4. Give a rational function where the graph goes up on both sides of an asymptote. Also give one where it goes down on both sides. So far we've always seen our asymptotes where on one side it goes up and the other side it goes down, or maybe the other way, right? But is it possible to create something where it's going to go up on both sides, or going to go down on both sides? So let's look at our first one that we think. When we think rational function, we immediately think, oh, the fundamental, the basic thing that sort of makes up rational functions, 1 over x. This is the simplest form we can think of that really shows these ideas we're looking for. 1 over x winds up giving us a graph that is that gets very, very large, that gets to the right side, but goes down on the right, and then same thing, blows down. So the issue here with 1 over x, the issue is on one side, it's negative, right? On the left side, we were dividing by negative numbers, so we've got negative. On other side, it's positive. So that's why we go up and down. So that's what causes up and down effect. Well, down and up if we go negative to positive. But that's why we're seeing this split where we're going in two opposite ways. Because on one side of the vertical asymptote, we're dividing by a negative number. On the other side of the vertical asymptote, we're dividing by a positive number. They're both very small numbers, but that negative versus positive, that causes this incredible difference in whether you go to negative infinity or positive infinity. So what we want is we want positive on both sides if we're going to go up on both sides. So what could we create that would be similar to 1 over x, but always putting out positive things on the bottom? So let's keep it as 1 over. But what is always positive? Well, instead of dividing by x, let's divide by x squared, right? We can force it to always be positive. 1 over x squared, still a polynomial, so we're still a rational function. And if we draw that one in, we're going to see it behaving very similarly on the right side. It will wind up being here and here and here as we get to small numbers, right? As we get below 1, we're going to be getting to dividing by very small numbers, so it's going to blow out to infinity. And it will get crushed down to 0 as it goes to the right. On the left side, though, when we square a negative number, it becomes positive, so we're going to see a mirror image on the left side as well. So we're going to see it going up on both sides. If we want to get one that's going to go down on both sides, if we want it to be down on both sides, well, we see 1 over x squared. We just want it to go down, so let's make it as easy as just flipping it down. We flip it down by making everything negative, so negative 1 over x squared, and we'll see a graph that looks like this. We've managed to make it go down on both sides. So a simple way to make it go both sides go in the same direction is by having it be squared or having it be negative and then squared. Great. Not negative and then squared because that'd be positive, but a negative square because then it's a square number times a negative. Cool. All right. We'll see you at educator.com later. Next time we'll talk about horizontal asymptotes and have an understanding of why it's getting crushed to 0 and see that it can in fact be crushed to values other than 0. Pretty interesting. Bye.